So, good morning, everyone. Welcome to this second talk in the public outreach series of IISER Mohali. Today, we have Professor Arvind with us. So, Professor Arvind works in the Department of Physics at IISER Mohali. His area of interest in terms of research is quantum theory. He works on a wide range of topics, including quantum information, quantum computing, the basic idea and the foundations of quantum theory itself. In terms of his broader interest, he's also interested in teaching and communication of science. So he also does a lot of development of new experiments to teach physics, for example. So he is a man with a very wide range of interests, and today he will be talking to us about what is quantum information processing. Now, before I hand it over to him, a few requests. Please keep yourselves on mute all the time. We will take questions at the end. You can use the raise hand feature after the talk, and we will let you ask your question if you are on the Zoom. If you are on YouTube, you can type in your question in the comment section, and we will pick up the questions from there, and they will be asked here by the moderators. If you are unable to ask on Zoom, please again use the chat feature to ask the questions. Okay, thank you, Professor Arvind.
Good morning, everyone, and thank you very much for arranging this talk today. I am very happy to give the outreach talk today, the public outreach talk. And Dr. Prasad has already introduced the idea and so on. Again, Dr. Mahua and Dr. Amit Kulshrestha, who are the hosts and moderators, I thank them for the work they have put up in setting this all up. See, quantum information processing, everyone has now heard of, and many people call it quantum computing or quantum computers. I'm going to tell you a little bit about it, what this subject is all about. More than that, I'm going to tell you what is the quantum view of the world, which today is revolutionizing information processing in terms of giving us new possibilities for building computers and communication channels and so on. Let me first begin by telling you that at IISER Mohali, we have a very large set of people who are interested in quantum ideas and ideas related to quantum information processing. So we have a Center for Quantum Foundations and Technology and Application. There are several faculty members, postdocs, PhD students who engage in this work. And later on, as towards the end, I will tell you that there is a national mission on quantum technologies which is coming up. And one of the consultative meetings of that mission program was held at IISER Mohali in November 2019, and this is a picture from that. So this gives you an idea that at IISER Mohali, we have a very strong activity in the areas of quantum information processing and quantum foundations. The quantum mechanics or the quantum view of the world came about in 1920s, and the observations on atomic spectra, black body radiation, and photoelectric effect were the phenomena or the observations which led to the construction of this new way of looking at the world, which we call quantum physics or quantum mechanics today. To give you a little bit of a glimpse of the kind of contradictions which existed at that time in terms of observations and our theoretical understanding, let me tell you that toward the end of 19th century, it was felt that we are going to know everything about the world around us. So Lord Kelvin gave a talk where he said that end of physics, most of the things are known, few problems he listed, and once the answers to those problems come, we will know everything about the physical world around us. However, very soon, observations about the world told us that we could not explain them. For example, if you heat metal, it emits light. We all know hot objects have a certain color coming out of those. And if you heat specific elements, there are specific lines or spectral lines which come out. And other frequencies, other colors don't come out. For example, neon has that specific crimson kind of light. Sodium has a yellow light associated with it, so on and so forth. So there is specific characteristic spectral lines or colors which come out of matter when it is heated, depending on which element it is. Now, heat is a random phenomena. Heat is random motion of atoms. And if random motion was just in a classical way leading to motion of charges, and those motion of acceleration of charges was giving rise to this light, then we should get all kinds of light, not specific kind of light. So this was a puzzle which could never be explained using classical ideas of 19th century physics. Similarly, if you have a black body like sun and you look at the spectrum means that you look at the energy density at a given frequency, how much red light is coming, how much yellow light is coming, how much blue light is coming, and so on. So then you can plot a graph. There is a specific color at which the intensity is maximum, and that is dependent only on the temperature of the body. So the information about the temperature is encoded in a specific color having the highest intensity. And again, this feature could not be explained using classical physics. In classical physics, either the energy density should go up and up and up with frequency, or in another calculation, it should go down and down. So this whole idea of it peaking at a particular color is something which could not be explained using classical physics. And the third important thing which you must have heard of, that when a photon hits an electron in a material, in a metal, say, and kicks it off. Now, this whole picture that photon acts like a particle which kicks off an electron is the only way we can explain it. Using earlier way of looking at light as waves, where if electron should keep absorbing light and at some time it should get ejected from the material, that does not seem to happen. If the frequency of light is lower than a certain threshold frequency, you can expose metal to light forever. A photoelectron will never come out. So such were the contradictions which existed between observed phenomena and our understanding of physics at the end of 19th century or in the beginning of 20th century. And this led to construction of a new way of looking at the world, which we called quantum physics. Now, 20th century is called quantum century. So all material properties, practically all chemistry, because chemistry depends on chemical bonds and how atoms interact with each other, and that's completely non-understandable using classical physics, because orbitals, electron densities, all these are quantum notions. So 20th century has seen application of quantum ideas to atoms, molecules, nuclei, solids, particles, and so on. So the particle physics, which is a very well developed field today, is basically an application of quantum mechanics or quantum way of looking at the world to fundamental particles. So this is in some sense, in nutshell, the history of physics of 20th century is the history of applications of quantum mechanics in various areas of physics. Now, this new way of thinking, which we call the quantum way of thinking, is it just another equation? Is it just another way of writing down? Like we had Newton's laws, which were developed in 17th century. Then we had thermodynamics, which came later, which has its own equations. And then we had Maxwell equations describing electromagnetic phenomena. Now, of course, discovery of electromagnetic phenomena and construction of an explanation using Maxwell equations was a very, very big development of 19th century physics. But the way of thinking more or less remained the same. So, classical way of thinking, which we call. The new way of thinking which came with quantum physics is very bizarre and very different. And I want to give you a little bit of glimpse into that. So in classical world, we define situations as per our intuition. So, well, what do you say? I say a particle, you can close your eyes, imagine a particle. I say a force acting on a particle, you imagine a little push or a vector in a certain direction. Particles begins to move, you talk about motion on a trajectory. So all this you can think in your mind. Even when you say there is electric field, you feel electric field is defined as force on a unit test charge, which is placed over there. So a small little vector associated with the field you can imagine. On the other hand, in the quantum world, situations may not be as per intuition. When somebody says sp3 hybridization, I hope you all have heard of chemical bonds. Or somebody talks about tetrahedral structure of carbon, and in methane you say in the corners of those tetrahedron hydrogens come and get attached. There are only 4 electrons in carbon. How can they be forming a tetrahedral structure and sp3 hybridization where we say these 4 electrons are delocalized and they are everywhere around, and we talk about such things? When we talk about a p orbital, we draw this p orbital and we say this electron is in the p orbital. Where is that electron in that p orbital if it is a point charge? Answer is we don't know. We associate that orbital with that electron, and that is what is the correct picture to imagine that particular electron in that atom. So intuitively, if it is a particle, how can we associate it with a delocalized orbital remains completely unanswered and elusive, and we have to accept it. Why we have to accept it? Because this is the only picture which gives us the correct properties of atoms, their interactions, and so on. So one major difference is that intuitive way of picturing phenomena and situations does not work in quantum physics. The second aspect is probabilities. So in the classical world, probabilities represent lack of knowledge. For example, if you go to CAF building where my office is and somebody says, is Professor Arvind here? The person over there will say, oh, probably he didn't come today. Probably he is at home. Or probably he's giving a webinar, or probably maybe he's sleeping, he just didn't get up. So these are all possibilities, and we assign possibilities to these probabilities to these possibilities. However, Professor Arvind as a single individual will do only one thing at a time. So, for example, if the same question is asked to Dr. Amit Kulsreshta or Dr. Mahuagara or Dr. NG Prasad or any of you, you will say, Professor Arvind, he is talking to us and giving a webinar right now. So there is no probability. There is only one possibility with probability 1. So in the classical world, under probability, there is a layer of certainty. We know that things are happening in a certain way. Since we don't have knowledge about them, we are representing them through probabilities. Let me give you another example very quickly. If you open, if you have a molecule which emits, say, UV radiation. UV radiation we can't see. And these days you have these tweezers in which you can hold a single molecule. So I'm holding that molecule in my hand, nobody can see. But one of you have a detector which can detect UV. So when you see through that detector, or imagine that that is like a binocular. So you wear those binoculars, one of you have them, you can see that molecule in my hand. Then I release the molecule. Molecule goes here and there. You stop seeing through binocular. After 5 minutes, you ask everyone, where is the molecule? People say it has equal probability to be everywhere in the room. It cannot leave the room because room is closed. So it is somewhere in the room. We don't know where it is. It's equally probable everywhere. Now we go back to the person with binoculars. Person with binoculars looks at through the binoculars and say, what are you talking about? It is actually in that corner. It is not anywhere else in the room. So since it is one molecule, it will be in one place. That intuitively we know. And that since either it's a lack of knowledge or that information is too difficult to describe, because if there are billions of molecules, saying which one is my molecule become too difficult to even write down on a piece of paper. So either we don't want to process that information or we don't have the information, but we always think that there is a layer of certainty which exists, and we assign probabilities to represent our lack of knowledge. This is the understanding of probability we have in the classical world. However, in the quantum world, probabilities become fundamental. For example, if I have uranium and there are two nuclei which are kept on the table, and they will decay into another element through radioactive decay. Now, let's assume that probability is half-life is 5 minutes. Then after 5 minutes, there is a good amount of probability that one of them will decay. You can calculate it. By the way, it is not that after 5 minutes one has to decay. There is a strong probability, which is about half, that one will decay. The question is, which one will decay first? So you set up this experiment many times and you say, oh, left and right. So will left one will decay first or right one will decay first? Well, nobody knows. Quantum mechanics doesn't tell you, but It is more fundamental than that. There is no other way also of finding it out. So nature intrinsically is probabilistic. This probability is not based on our lack of knowledge or a lack of theory that we are not able to predict, but someone knows. No one in the universe knows which of those two uranium nuclei will decay first. And that is the kind of situation we have to accept some other time. But this is what made Einstein feel very uncomfortable. And he said, God cannot be playing dice. So Einstein was very uncomfortable with probabilities being fundamental. He thought that probabilities should come the way they come in classical physics, which means as lack of knowledge. And therefore, he encouraged people to come up with better understanding of the world, where these probabilities disappear and we base our understanding of the world on certainties. This was in 1935. By 1965, people realized that such attempts cannot succeed. There are fundamental problems with such attempts, and we have to accept probabilities as fundamental way of nature being uncertain. Anyway, the third contrast which I want to tell you about is the space of theory and actual space. So in classical physics, normally you say, oh, let us think of a system, let us think of space, configuration space, this, that, and so on. In quantum theory, we have to move to a different space, which is sometimes finite dimensional, sometimes infinite dimensional, complex linear vector space. We do all our theory there, and that space has nothing to do with the phenomena that we are explaining. It doesn't. That space doesn't look like atoms and molecules and particles. It is an abstract space. We do calculations in that space, and then we come and compare our results with the experiments which we do in the real space. So it's a meta theory. It is abstraction or theorization one step further than regular way of theorizing, where you put in motifs from the actual world and begin to look at regularities and write equations for the dynamics. You have to take the whole problem in a different mathematical space and do your calculations over there and come back and make comparison. This is somewhat related to the first point, that intuition doesn't work, but it is much deeper, that you cannot even construct a mathematical model which looks similar to the phenomena that you are explaining or working with. So you can see the quantum way of the looking at the world is quite different. Let us look at few more contrasts between classical and quantum. So classical world is continuous, where quantum world is discrete. That's very important. Every photon is a discrete packet of energy. Electron cannot be further divided. Even its charge, mass, all that is fixed. So fundamental motifs of the universe are discrete and not continuous. This is one conclusion which comes from quantum way of looking at the world. The second one is superposition principle. So superposition principle is the following. If situation A is possible, situation B is also possible. In the classical world, one of them can happen. In the quantum world, both can happen together, which means a quantum particle can be in more than one places at the same time, and so on. And not just that, a quantum particle can have more than one momenta at the same time. A quantum particle can have more than one energies at the same time. It's a very broad general principle that whatever is possible one by one is also possible together, all simultaneously. This is called superposition principle. Of course, some of the possibilities cannot be superposed, but that's a technicality which we call super selection rules. But in principle, the logical or classical possibilities can be superposed and they can exist together. We'll come back to this in many ways, because this is at the heart of many of the non-intuitive features, and also at the heart of being able to do information processing using the quantum world. The third contrast with the classical world is measurements. So in classical world, measurements come at no cost. No cost means I can learn about an object without interfering with it. So measurement process is a passive process of learning. To give you a very direct example, you go to library, you issue a book, you read that book, you put it back. I go to the library, I go and I read the same book. So no change in the book happens because you have read it, unless you tear it and you write on it and so on. But let's assume you're a good student and you don't do any of that. However, if it is a quantum book, the process of your reading it No way you can read it without changing it. So the book I read when I issue it second time is slightly different from the original book. So no one can passively learn. You have to engage, and in that engagement process you end up changing or modifying the object about which you are learning. So this is also a fundamental principle of quantum physics, and this comes very handy when we are trying to do secure quantum communication, where we have someone trying to eavesdrop on our conversation. Now that person cannot passively listen. The presence of that person will be seen in our channel, and in the quantum cryptography, that's what we do. We end up detecting the presence of an eavesdropper using this fundamental principle of quantum physics. Sometimes this also goes by another principle called no cloning theorem. I'm not going to talk about that, but I will tell you no cloning theorem basically means that you cannot make copies of a quantum state. So the same thing, right? If you see, since, for example, if I could make copies, then I'll make copies. You go and read one copy of the book, I will read another copy of the book. So I can circumvent the measurement problem, but that also is not allowed. So all this ties in with each other. The last contrast that I'm going to mention is quantum entanglement, which is a very, very fundamental quantum feature which does not exist in the classical world. I know by now you have many questions. Keep your questions, write them down. I'm not going to talk for too long, and I will answer all your questions and engage with you in a full fledged detailed discussion, which is the way our outreach program works. Now, what happens is that in physics, particularly after Einstein's theory of relativity, we think about local description. So local description means the following. So sitting here talking to you, I cannot hit you because the word is local. I can talk to you, even my voice reaches to you after some time. I can't even influence your thoughts because nothing propagates faster than light. So any word I utter which can in principle influence you, if you are at a distance L, it will take time which is L divided by velocity of light. That much time it has to take for any information from me to reach you. So it depends on whether you're 100 kilometers away, 1000 kilometers away, logged in from where, and so on. Which means that your phenomena nearby only can influence you directly. So this is called principle of locality. And if you see, it's very important. If the word was non-local, we won't be able to do anything. You want to set up an experiment in your lab, but someone in another part of the universe disrupts your experiment. And there are so many people, so many influences. So I think you will not be able to do anything in a systematic way if the word was not local. So it protects us in many ways. So, although Einstein discovered it and formulated it in the beginning of 20th century through special theory of relativity, now when you look back by hindsight, without locality, we can't function. You know, my thoughts can be controlled, various things can happen. I can never do an experiment the way I really want to do. Now, what quantum entanglement says is that while locality is there, I can do something very interesting. I can make predictions about your outcomes of your experiments, which are probabilistic in nature. Remember what I'm saying. So you are doing some experiment, which is probabilistic in nature. But if my system is entangled with your system, I may be far away, not being able to influence your laboratory, but I can make predictions about your experiments, which you have not yet done, even before you, and I will know what you will get. Very interesting. So you don't even know what you're going to get because you are working with a system whose outcomes are random. And you only know that one or the other outcome is going to come with certain probabilities. But I can, sitting in my laboratory, make predictions about your location. This is what is called quantum entanglement. It has very interesting consequences. It basically comes in the way of completing Einstein's project of finding a better theory than quantum mechanics, which would not have probabilities. So it's again a very, very fundamental principle. And that principle is again very important in doing quantum information processing using quantum ideas. I must also tell you that In some sense, it is a consequence of superposition principle. So entanglement is a special kind of superposition which can exist and which can be harnessed and used in the way I mentioned to you. So as you can see, the quantum logic or the quantum word is very different from the classical word. Now the question is that most of these things were known for a long time. Why are we talking about quantum mechanics again in 21st century? After all, these ideas were developed in the beginning of 20th century, and people have engaged with these ideas for about a century. So why is so much new excitement about quantum physics or quantum way of looking at the world? Well, there are three reasons I'm telling you. There could be many more. First of all, most quantum phenomena are microscopic. So the different logic or the bizarre properties or this whole thing of being present in more than one, this happens inside atoms and nuclei and so on. And I don't need to worry about it because it happens at the end of the day. It gives me certain stable motives to work with in the world. And in that process, then I don't really engage with it very directly. What has happened toward the uh, end of 20th century and beginning of 21st century is that people have managed to create situations in the laboratory where such things happen at scales in which we did not think that they will happen. So it is not just the microscopic world. Quantum ideas may be important for the macroscopic world. We may now be able to create situations which would be quantum in nature, but would be at time scales and length scales at which earlier we could not see these things. All right. So it is one thing to create superposition of an electron inside an atom, but it's another thing to create a superposition uh, of an electron over say 10 microns, or at the end of the day over kilometers. So then that would lead to situations which will be non-intuitive, and we will be forced to engage with them. I mean, a new subject is emerging called quantum biology. So, well, you can argue that biology is all based on chemistry. Chemistry is all quantum. Therefore, all biological systems are quantum because the chemical bonds and chemical exchanges play an important role. Of course, that is true. But today, what people are finding out is that within biological world, there are phenomena where organisms use quantum mechanics operating at larger scales, at scales which we don't expect quantum phenomena to survive. And macroscopic quantum phenomena is being used like avian compasses or photosynthesis. So there are situations within the biological world which is harnessing quantum phenomena at the macroscopic level. So that is why a new interest is there in quantum physics again at end of 100 years. Of course, the last one and the most important one is that in the 21st century, people feel that we may be able to process information using quantum ideas in a new way. So let me give you a little bit of a introduction here. See, the idea that well, maybe I'll come to that later. So that is what I had given as my title, because you see, in a very broad sense, if I can exist in superposition of different possibilities, can I do parallel computations? Can I compute? I want to compute something over 100 inputs, 1,000 inputs, billion inputs, instead of doing it one by one or employing that many processors or threads. Why can't I use the principle of quantum superposition and somehow compute all those things and then combine them in one go? Such possibilities are opening up and are being harnessed to do information processing. So in quantum information processing, there are three sub areas which are becoming very important. One, of course, is quantum algorithms. So quantum algorithms is where you use quantum ideas to solve problems which cannot be solved using classical computers. I will give you examples of such problems very quickly. Other one is quantum simulations, because it is well known that to do calculations about quantum systems, it is very difficult to do it on computers. As the system size grows, the computations become undoable. So if we have quantum information processors, there might be motifs which can be used to understand larger quantum systems. So idea is take small quantum systems, couple them together, use them as a computer to understand larger quantum systems or perform quantum simulations. And the third one is quantum cryptography, which is an independent development. Secure communication, it has been shown, can be done only using quantum physics. Within the classical world, we don't have secure communication. So for security of communication or for cryptography, quantum physics comes in handy. So I will mention some of these things in some detail at a very broad level today, and maybe later in some more technical detail. Before I get into those details, let me tell you a few more things. So, a very well-known scientist has put it as gifts of quantum mechanics to nature. So, stability in the classical physics thought that hydrogen atom or any atom will not be stable because electron will slowly lose its energy and run into the nucleus. So, quantum mechanics told us how the word is actually stable. The stability of the word is understood by quantum mechanics. Countability. Quantum itself means discrete. So counting, otherwise the things were supposed to be continuous flows and so on. The idea that the world is made up of discrete objects and countable objects is fundamentally quantum. Then, of course, information. So, information storage and processing using discrete motifs like bits and qubits, large registers like DNA, and so on. Again, is a idea of in using information in a discrete way. And people are also thinking that maybe information processing at a fundamental level inside biological systems might have certain quantum processes behind it. That is somewhat speculative, but still idea is around. Randomness. Word being random, probability being fundamental, is something which was not at all thought to be important earlier. And quantum mechanics has brought randomness in the universe as a fundamental acceptable principle. And of course, this randomness leads to possibilities. So, as Darwin taught us, life without variation is not life. So, variations in outcomes, you don't only have one outcome at the end of an experiment. To have it even in the physical world, quantum mechanics brought it onto the forefront. There is an important article which I read recently, which says that the idea that this probabilities could be fundamental in biological systems also became much more acceptable somewhere at the same time when they became acceptable in physics. So even at the level of progress of civilization thought in terms of accepting randomness as a fundamental principle happened in the beginning of 20th century. There might be variations in different philosophers might have thought differently, but this is how I would like to put it for today's talk. So this part of the talk, maybe I will end by saying that quantum physics or quantum mechanics has given us a very, very new way of looking at the world and has revolutionized our thinking about the world around us. And at the end of 20th century and beginning of 21st century, it is moving into revolutionizing the way we do perform information storage and processing tasks. Now, interestingly, computation, machine computing, any object outside human mind being able to do engines and railways or many other things were known in the 19th century, but the idea that machines could compute is primarily a 20th century concept. It started in 20th century, even theoretically, then people build mechanical models, this, that, and so on, and finally the modern computers. Well, it's very interesting. Quantum physics also is 20th century phenomena. Computing by machines is also a 20th century phenomenon. But they remained parallel for about 100 years. And now as I show you how they are coming together. But when you compute, since computation is no longer something that you're unfamiliar with, some problems are easy, some problems are difficult. So for my rest of my talk, it's important for you to have an intuitive feeling for what is the meaning of an easy problem and what is the meaning of a difficult problem and how roughly can we quantify the degree of difficulty of a computational problem. Let's see. You see, the problems can have a size. Same problem can be done at one size, next size, bigger, 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 bigger. And normally one wants to know how does the time taken to solve the problem changes with the size of the problem. So let me put a very simple problem to you. Is a number even or odd? after thinking about for 10 to 15 seconds, most of you are smart people, you will see that to figure out, I don't even need to know how big is the number. Whether number is a 10-digit number or a 4-digit number or 100-digit number, it takes me roughly the same amount of time because I only look at the last digit, and last digit tells me the number is even or odd. So which means this problem is very easy. It scales very nicely. I keep changing the size of the problem, but the time taken to solve the problem by me or by a computer does not change at all. So the time is t for any size of the problem. What about addition? I want to add two numbers. How difficult it is? Is it as difficult? Does the size time taken to add two numbers grows as the size of the number? Hold on. I add 4 plus 5. I add 7 plus 8. Well, roughly at the same time. 11 plus 13. 18 plus 15. Looks like, if you think about it for another 10-15 seconds, the time taken is more like addition operations, and they are proportional to the number of digits in the number, not the number. A number of digits in a number is log. So this problem is also not too difficult. If I have a number which is, in billions, the time taken to add such numbers will not grow as billion. It will grow as log of billion. So log of, is a much smaller number. So, so 1,000, 3-digit numbers go all the way up to 1,000, right? 4-digit numbers go to 10. So like that. So it is all, so the time taken to do addition goes as log of the number which we are adding. So it's also grows much slower than the number. Multiplication, you can figure out how many operations, all that will give you some other function. So this way I can find out, I can write down a function, time taken to solve a problem as a function of the size of the problem. And that tells me how difficult or easy is a problem. If the function is a polynomial function, those problems are called polynomial complexity problems, and those are considered solvable in computer science. If the number is exponential function of the size, such problems are called very hard, they are not solvable. And that's easy to see because exponential 2 to the a to the x or 2 to the n grows so fast that you can beat any computer very quickly. So you can see 2 to the 2, 2 to the 3. How much is 2 to the 10? 2 to the, if 2 to the 10 you can solve, I'll give you 2 to the 20. So you can, if a problem has an exponential dependence of time on the size of the problem, it is called non-solvable, although I know the algorithm. And non-solvable means that the fastest computer in the world can be beaten very quickly by just adding one digit to the size of the problem. I'll come to examples of such problems very soon. So this you have to internalize, that there are problems in computation which are easy, there are problems in computation which are difficult. And if the time taken to solve a problem is an exponential function, like x is the size of the problem, x to the power t. So that kind of problem is, sorry, yeah, so it goes exponentially as the size. So the x will be in the exponential. So a to the power x. So a is some fundamental unit, and the size of the problem is in the exponential. Such problems are not just hard, they are considered exponentially hard and therefore not solvable. So let's look at a problem. See, multiplication we all can do, and it's not very difficult because we do it on paper, computers can do, and so on. What about opposite of multiplication, which is factorization? Turns out factorization is exponentially hard. I will not get into technical details, but to give you an example, I have written a number. So what is this number? Well, 156053. It is a 6-digit number. It's not very large number. Many times if you multiply numbers, if you multiply say a 4-digit number by a 3-digit number, you can easily get a 6-digit number. So multiplication wise, such numbers are very easy. I mean, I say 2568 multiplied by 1201. A number you will get will be larger than this number. Right? So such numbers are easily handled when we multiply numbers. And my question to you is, I have given this number and I am claiming it is x into y. Can you find x and y for me? So if I give you 2 minutes, 3 minutes, 5 minutes, unless you are somebody like Shakuntala Devi, you will not be able to find X and Y. And if you find, I allow anybody who finds it within few minutes without using any other device, I will tell the host, let him unmute his mic and say something. Doesn't matter. We will violate the rule of not muting the mics. All right. So you will try and you will see that the reverse of multiplication, which is factorization, is actually not simple. It's a very, very hard problem. It's exponentially hard problem. If you are able to solve this, I'll give you a number which is 1 digit bigger, and that will be order of magnitude more difficult to solve. And very soon, if I write a number which is say 12 or 13 digits, which is not very far-fetched, even the fastest computer in the world will not be able to solve this problem in the life of the universe. So you can easily write a number on a piece of paper or on the blackboard whose factors cannot be computed by fastest computer in the world, even if you allow that computer to work for the age of the universe, which means 10 billion years. So you see how easily one can come up with mathematical problems which are well defined, but to actually do them is impossible. So this is the beauty. Multiplication anybody can do, factorization is exponentially hard. And you will have to get used to it. If you try it out, you will see what I'm saying. Let me give you one more problem. Uh, okay, before we go to the next problem, uh, why has there been so much interest in quantum information processing? See, in the end of 20th century, a scientist by the name of Peter Shor proved that if you can build a quantum computer, you will be able to factorize large numbers in polynomial time, which means something which is impossible to do by classical computers like factorization, you will be able to do it on a quantum computer once that computer is built. Of course, it will use those non-intuitive concepts of entanglement and superposition and measurements and all that in a very non-trivial way. So that led to a lot of development, and we will come to the state of art later, how things are moving. So this is one problem which is not doable on a classical computer, but quantum computer when built or quantum information processor when built will be able to solve it. Let me give you one more example of a problem. So this is database search. So you have a database, you want to search it. Of course, if database has a structure like a telephone directory which is arranged by alphabetically, it's very easy to search. So structured database search can be done in log n steps. You can easily convince yourself. Why? I take that whole directory book. So first, if the name is say Piyush, I know it is in P. So I open it on the P side. In the P, I say, oh, PU. So I go for that. So very quickly I search, I divide the problem into first a P segment inside the U segment, like that. From the spellings, I'm able to find the number very quickly in roughly in log n steps. However, if I give you a number and ask you to find the name, that is actually quite difficult. Whose number is 293566878? That's very difficult. How do I know where to look? So I have to roughly, on the average, if such a problem has to be solved, I have to look at the whole directory. So therefore, unstructured database search is hard. It is exponentially hard because, as you know, that capital N data entries can be encoded in log n bits, and therefore, in terms of number of bits required to encode the database, the number of queries will go as 2 to the n, which is goes as capital N. So if the telephone directory has a million entries, you will have to, on the average, search 500,000, because sometimes your number will be found easily, sometimes it will be very difficult because it might be the last number. So on the average, you have to engage with the entire database, which means the queries you make, the number of times you consult the database is order n, which is exponential in the number of bits in which you encode the database. I hope you are able to hold these ideas in your mind, but if there are questions later, we will come. So this is also an exponentially hard problem. Came a quantum solution, which is not that it can be done in polynomial time, but an Indian scientist of Indian origin, Love Grover, who did his BTech in electrical engineering from IIT Delhi and later on was working in Bell Labs, found a solution to database search problem which requires root n queries on a quantum computer. So root n, of course, if n is exponential, root n is also exponential, but it's a major advantage. To give you an idea, root of million is 1,000. So something which requires million steps will now require only 1,000 steps. So this generated a lot of interest in computer scientists and other people in quantum computation, because today is not the time, but if you can do unstructured database search, you can solve many problems. Many problems in computer science can be reduced to unstructured database search. It also has very strong implications for P, NP, and NP hard problems. Those are technicalities which are not for today, but if there's a question, I will dwell upon them. So two major theoretical constructions or discoveries or creations were creation. Algorithms are creations, right? They're creations of a human mind. They don't exist in nature. Two algorithms were created, one for factorization and one for database search. Both the problems which are exponentially hard means are not doable on a classical computer, on a quantum computer. People said if quantum computers are built, they will be able to solve these problems. One, of course, in polynomial time, another one only taking square root of the steps which a classical computer will take. Now, the independent development came in cryptography. Here I'm going to go in little bit of detail because it's slightly more accessible and you will be able to understand, although I don't know how much time I have. Let me look at the time that will decide. Yeah, I don't have that much time, so I will quickly go through cryptography. So cryptography basically is a problem where Alice wants to send a message to Bob such that Eve cannot decode it. And who's Eve? Eve's an eavesdropper who's actually sitting somewhere and trying to listen to the conversation between Alice and Bob and trying to make out what they're talking about. In a typical war-like situation, Alice might be the general who wants to send to the front and say, start the attack. And of course, they don't want to know that the orders have gone. So one way is to code. Code means you shift the letters. So you see A becomes F, R becomes V, T becomes S, X. So what have I done? H becomes L, E becomes I. And the message which goes is this WX, FVX, XLI, FXX, FGO. And Bob gets this message. He decodes and gets the message, start the attack. And what is the code here? +4 cyclically. So I've shifted each letter in English to read it like this. Of course, the code will be decoded and orders will be executed. But the question is this secure? Because after all, I have used an algorithm to code. And Eve might try to do operations on the code word, which is this written in red, and try to get English back. And if Eve has a supercomputer and a large number of scientists working for her, there is a possibility that the code will be cracked. And once the code is cracked, all falling, and Alice and Bob are not going to exchange only one message, they're going to keep exchanging messages. So Eve will have a whole database of messages, will run all kinds of programs on this database, and she will find out what code is being used and therefore will decode it. So algorithmic codes, this is an algorithmic code. I have used an algorithm to code. Algorithmic codes can be cracked by learning process. Like we crack ancient languages, right? I mean, there are languages which are now, the language is lost. Only the written scriptures are there. From those, one is able to find the language. This kind of processes are done by linguists. And because there's certain logic. If there's certain logic, we can find out the code. I mean, in some sense, science is all about this. Look at the phenomena, look at regularities, and come up with the way they are organized through equations and explanations and all that and so on. However, if the code is randomized, first message was +4, second message is +3. So randomly we use code shifting, random shifts. That cannot be learned because by the time you develop certain intuition about what kind of code is happening, Alice, Bob will be changing the code. But then how will Bob decode? So Bob will have to have an information about how random numbers are being used for coding. So if Alice and Bob can have shared randomness, which nobody else shares with them, then they can do cryptography. So cryptography can be reduced to, to sharing randomness. And if I can secretly share randomness with you, then after that I can use it to do cryptography. This is called one-time pad. It's an old solution, mathematically profound solution. So therefore, one need not talk about cryptography. One needs to only talk about sharing randomness. Because if you can share randomness, you can do cryptography. Now, how do we share randomness? So I will tell you the quantum solution. I must tell you there is no foolproof classical way of sharing randomness. That is a detailed discussion, so I will not get into. I will just tell you such a solution does not exist within classical physics. Using quantum ideas, we can do it. First, let's translate the problem into binary. So English can be coded in binary. As I've shown you, A becomes 0001, B becomes 00010. So 5-bit code can code English. Once you code English, the message is an n-bit binary string. And you generate a random string by coin toss, add random string to the message string, and you will get the code string. Now this code string is as random string. Therefore, Eve cannot decode anything, cannot learn anything from there. On the other hand, if Bob has the random string, which was the key string, he can subtract it from the code string and get the message string. This is just, I'm repeating what I said in the earlier slide, using more technical language of binary. This is called a one-time pad. So one-time pad is fundamentally secure. Now to distribute, and the problem of sharing randomness technically is called key distribution. So there are classical ways of distributing keys like RSA. I thought I'll explain RSA today, but time is not really permitting that. But all classical ways of exchanging keys or distributing key is fundamentally insecure. And the solution which comes is a quantum solution. Let me describe to you that quantum solution. So qubit is a two-level quantum system which provides the fundamental motive for quantum communication as well as quantum information processing. And I take 2 qubits and I put them in a state written in the second line, which is an entangled state. So what does it say? It says that I have a two-level system, Alice has a two-level system, Bob has a two-level system. The state is such that, of course, my system can be 0, then Alice's system is 0, Bob's system is 1. So 0, 1. That's a possibility, you see. Now, other possibility is also there, that Alice's system is 1 and Bob's system is 0. This is also a logical possibility. Remember, quantum physics told us they can also be possible together. So when I put them together, I get a state called singlet state, which is written like this. It is also rotationally invariant, which means that, see, up is 0 and down is 1 because it's a spin. On the other hand, I can say, inwards is 0 and outwards is 1. Or I can choose any direction to call one up as 0 and down as 1. The state remains the same. So it's rotationally invariant, which means in whichever basis I write, it looks the same. And it has the same structure, which means now if I make a measurement on it, and in one measurement Alice gets 0, Bob will get 1, and if Alice gets 1, Bob will get 0. So you see, for Alice, both possibilities are equally probable because the amplitude in front of each component is 1 over root 2. And when I square it, the probability is half. So Alice gets 0 and 1 with the probability half. Bob also gets 0 and 1 with probability half. However, if they measure along same direction, whenever Alice gets 0, Bob gets 1. Whenever Alice gets 1, Bob gets 0. Now what do they do? So Alice and Bob generate long binary strings at their ends. They make public the random choices of axes. So Alice and Bob generate long binary strings at their ends, and depending on, so let me go back. So there are two bases they use. Sometimes they will make measurements along Z. Sometimes they will make measurements along X randomly. And this randomness, where does it come? They do coin toss. So independent coin toss. Alice does coin tosses in her lab. Bob does coin tosses in his lab. If Alice gets 0, she will measure her qubit along Z. If she gets 1, she will measure her qubit along X. And Bob will do the same. Let's internalize this process now. You see, they don't know what axis measurements they are doing. So they are getting completely random string 0 1 0 1 1 0 whatever. He is also getting a completely random string. Eve, what can Eve do? Eve doesn't know what measurements they are making. So Eve also will have to do something. We will come to that later. After doing the measurements, they will announce the X's information in newspapers for each other and for the whole world. Now what happens? You see, if you have two random strings, you can easily find out that they will agree on their entries half the time. So now they will know which half time they made measurements along same direction and which half times they made measurements along different directions. Whenever they ended up making measurements along the same direction, they will be correlated. If Alice has 0, Bob has 1. Whenever they did not make measurements in same direction, they will not agree. So they discard all those cases like ZX, XZ. They keep the cases ZZ, XX, and so on, and filter out the other half. Now you see they have correlated random strings, which they can use as shared randomness, and this will form their key. Now let's see Eve is there. So Eve is trying to intercept, say, Bob's particle and trying to do measurements. Since she doesn't know anything about what they're doing, she will also do random measurements. So what can be shown is that Eve, by making random measurements, will disturb their correlations. So they will see Eve's presence by not getting perfect correlation. So which means when what they thought was perfectly correlated will not be perfectly correlated. How to test? Generate a random sample set from the large data, compare that, and if that differs more than certain positions, then they know there is someone trying to intercept their line. So you see, passive learning of information is not possible in quantum physics, and that can be used to do quantum cryptography. So I have just given a example of a run, but the way it will look. So Alice generates the random binary strings. Bob does it. They choose the axes, do the measurements, and wherever the axes are same, the entries will be same. I put it as same. They will be opposite, but I have just put 0 as 1 and 1 as 0 for Bob so that you can see correlation. See XX00, ZZ00. Here it is XX11 like that. All right. So this is their string. So let me now end my talk by telling you some overall thing. See, when I got into this area in late 90s, a lot of skepticism was there that quantum computers will never be built. A very well-known physicist by the name of Landauer wrote an article, Quantum Computers is a theoretical construction. One should not bother too much about them because they can never be built technologically. Well, but I still moved into this area after my PhD. After a few years, people used to say 100 years, it will take a century, it will not be built in our lifetimes. All right, that is fine. In science, many things can happen later. It can happen in your grandchildren's lifetime. Then, past 5 years or so, things have become very exciting when people are saying, the experts are saying that quantum computers will be built in 20 to 30 years. Already you see this news itself is 5 years old. This year, IBM and Google have announced their prototypes. So quantum computers are going to be built in 5 years, 10 years, 20 years, 30 years, but in about 30 years, they will be a reality and they will be actually carrying out tasks which we want them to carry out. And this has become very exciting because very likely this will happen in my lifetime. So I will see quantum computers. You will definitely see quantum computers. And you see how situations in science change in 20 years. 20 years ago, people said never. 25 years ago, people said never. Then 20 years ago, people said, more than a century. But what has led to this change in thinking? A lot of hard work. Several Nobel Prizes have gone into the field of quantum control. And since quantum computers require very, very fine control of quantum systems, which is now possible, quantum computers are going to become a reality. Quantum communication devices, which are like quantum crypto devices, are already available. People have done secure quantum communication over hundreds of kilometers now. Even satellite-based communication people have set up. So that has already become a reality. Uh, the various physical systems which are used for building quantum computers range from photons, nuclear spins, superconductors, ion traps, even other solid state devices. So there are many physical systems which people are trying out to build quantum information processors, and different groups are working on different kinds of systems. And sometimes, one looks more promising, sometimes another looks more promising, and we don't even know today whether the quantum computer 30 years later will be based on nuclear spins or superconductors or ion traps or photons, or maybe all of them, or maybe none of them, and a very different physical system. So you can see the the field is at a very, very exciting juncture where people are making progress and also not knowing where things will go. In India, we have a lot of initiatives which are coming up. There is a Quest program, Quantum Enabled Science and Technology program, for which IISER Mohali is a hub, and we coordinate 23 projects from here in the area of quantum communication. National Mission on Quantum Technologies and Applications is coming up in a big way. It is several thousand crores which will be pushed into this area, where quantum development of quantum computers will be taken up. And NMICPS, National Mission on the Cyberspace Technologies, is also has a part which is quantum technologies. So these national missions, two of them will have a component, one a minor component, one entirely dedicated to quantum technologies. Activity in this area is happening across the country, and in the world as well as in India, we are moving ahead towards realizing quantum information processors in a big way. Thank you very much. Now the discussion will be coordinated by moderators. I thank you for your patience.
Thank you, Arvind. Thank you so much for a nice talk. Um, we will now open up the forum for questions. Before that, I have a few requests. One, I already see there are a large number of questions that have come on YouTube. I'm sure there are a large number of questions that are going to come here on the Zoom link as well. Since we want to take as many questions as possible, one, those of you who are going to ask questions on Zoom, please stick to one question and please make the question brief and as concise as possible. Second, if you're from IISER Mohali itself, you always have direct access to Professor Arvind. I'm sure you will see him walking around, and he's not the one to say no to any discussion. So if you can hold off your questions for a later on discussion, that would be nice. We would like to take questions from people who are from outside, preference wise. If you are a student, it would be nice to take your question first rather than from a faculty, right? Okay. All this just to make sure that all the interesting questions get answered and questions from younger people get answered. So Arvind, I'll start with a question that's from YouTube. This is Raghav. Raghav is an MSc Physics student at University of Madras. He's interested in quantum information, and his question is, can you please comment on quantum chaos and solving it using quantum entanglement?
Yeah, so quantum chaos is a field in itself, and it's a somewhat subtle area. So earlier people used to think that there is no chaos in quantum mechanics because quantum mechanics is a unitary linear theory, whereas chaos in classical mechanics comes from nonlinearity. Later on, people found that those nonlinear classical systems, when you quantize, have very unique properties. And those are signatures of classical chaos in the quantum world. And many times they are related with highly entangled states and so on, and Wigner distributions which look entanglement. Now, I don't know what he exactly means by solving quantum chaos. Quantum chaos is a field, and there are many problems in that field. People are looking for better and better signatures for quantum chaos. And yes, those signatures many times involve entanglement. They also involve another area called random matrix theory, and certain very interesting classification and characteristics of chaotic systems in the quantum domain have come in the past 10, 15 years. The expert in this area is right sitting next to in Madras, in IIT Madras. Professor Arul Lakshmi Narayan is the expert in this country who works in quantum chaos. So maybe you can contact him for more details.
Okay. Thank you. Next question is from Zoom, Dr. Mandeep. You can unmute yourself and ask the question, please.
So first of all, thanks for the nice talk. My question is that in the beginning you said that probabilities are more is the fundamental concept in quantum mechanics. Why are you saying like that? Because probability is derived from wave function. So probability amplitude or wave function should be considered as more fundamental.
Well, that is a technical part. What you measure is the probability. When a radioactive nucleus is going to decay and I'm going to assign probabilities to different outcomes, I don't care whether you model it by wave functions or you model it by some other theory.
But Schrodinger equation
No,
is
wait. Schrodinger equation is theoretical construction. I am saying, is the probability fundamental or is it coming from another level in which there is certainty? So I'm distinguishing two situations
yes.
where probability is introduced to express lack of knowledge and where probability has to be introduced as a fundamental concept. It is
Okay.
nothing to do with wave function or one way of modeling or one equation.
No. All right. That is according to Copenhagen interpretation. If you go to Everett interpretation of quantum mechanics, there is no probability. So your notion
First
of
of all,
probability.
no. Everett interpretation has no measurable consequences which are different. There are people who don't believe. It's a question of belief. I am talking about a question of compulsion. Am I forced to say that probability is not fundamental? Quantum mechanics does not force me to say.
Can you
Still there may be people who believe that there is no probability in the world, but that is their belief.
Okay, so let me ask you a question this way. Can you go back once you have a measurement? Can you reverse your experiment?
That's a different question.
No, it's related to that. It's depth-wise, it's related to probability question. That probability is not that fundamental.
No, probability is fundamental in quantum mechanics.
Probability amplitude is fundamental.
No, that is technicality.
No, that's the foundational concept. Probability amplitude.
That is not what you measure in the laboratory. You measure probability. So I am talking about a black box theory, whether it forces you to keep probability or it says that probability is a tool. Quantum mechanics forces you to say that probability is fundamental.
I'm sorry to say, quantum mechanics is not saying like that. I'm sorry for that.
That is your way of looking at it.
No, there are many scientists believe like this, more than 80%.
Well, I see that this is going to be a discussion, so I would rather move on and take another question. Thank you, Dr. Mandeep. Loveleen, you could unmute yourself and ask your question.
Good morning, sir.
Good morning.
Sir, actually in the starting of this discussion, you was talking about some theorem, according to which you were saying that copy of system cannot be created.
Yeah.
But the definition of expectation value talks about the ensemble, that we are calculating expectation value from an ensemble. Ensemble is nothing but the copy of system that we are preparing.
Yeah, that's a very good question. So if I want to create an ensemble of identical copies, I can. But I cannot copy unknown states, which means that if I know what I'm preparing, I want to prepare an ensemble of systems in a particular state, I can do that. But if you say that I have a state which is in a black box, it is psi, and I don't know psi, take one psi and give me two psis, that cannot be done. That is no cloning theorem. So
that means something unknown.
Yes, unknown states cannot
certain.
be copied, whereas states which are known can be, of course, copied. And another way to produce identical ensembles of systems is through a measurement process. So when I measure, I can put different filters and filter different outcomes. For example, if a state is a superposition of 0 and 1, I make a measurement and put two boxes. All the outcomes with 0, I put them in one box, and all the outcomes with 1, I put in the other box. Now you see, I started with some state which I didn't know, but now I have two boxes where first box has all the states, all the systems in one state, which is 0. The second box has all the state with the systems in 1. So now I have created a pure ensemble of copies of 0. Now what I can do is I can bring in a unitary transformation which will take 0 to psi, and I will take every member through this process. Therefore, now I will have a box full of identical systems where every member has a state psi. So this way you prepare boxes or ensembles starting with a known state.
Okay, sir. Thank you, sir.
Professor Gauri Shankar, please go ahead.
Yes, Professor Arvind, thank you for this explaining this. My question is the following: that it looks like quantum computing actually does a double whammy as far as what I would call information processing and communication is concerned. In that, by solving this so-called unsolvable prime factor factorization, it makes existing systems very unsafe, even as it gives a new system for safe information processing. Can you comment on that?
Yeah, so, well, I didn't want to do overselling, but what you're saying is right, that a lot of people, see, once you have a quantum computer and once you can do prime factorization, the existing code, particularly what is called the RSA code, can be broken. So if RSA code is broken, lot of communication protocols which we are using currently will become redundant. They will not be no longer be secure. So immediately you have to look for new secure protocols. They come in two categories. One is called post-quantum cryptography, which are classical protocols which at the moment we don't know can be broken by quantum computers. But a more fundamental solution is quantum cryptography, which is fundamentally secure, which means that it doesn't require us to put a bound on the technology available with Eve. They are secure because of certain principles of quantum physics. So that's a fundamental security which it offers. So yes, so quantum computer will break the current security and then quantum solution for security will replace.
So is the RSA going to be broken earlier than the new system coming into place?
Well, people are already bringing in new systems. Now people say that RSA is broken if we have a quantum computer. So quantum computers are becoming a reality, although the kind of quantum computer which IBM or Google have built is not yet close to breaking RSA. But it will happen. Very soon people will have quantum computers which can break RSA.
Thank you. The next question is from a student of BSc Psychology from University of Hyderabad. Prashant, please go ahead.
Hello, am I audible?
Yeah, Prashant, please go ahead.
So that was a wonderful talk. So I have certain interests which push me into this realm. So excuse me for my lack of knowledge thereof. So I wanted to ask, given that quantum entanglement as a phenomenon exists or can be realized, can it be said that information travels faster than light, or is it capable of traveling faster than light? Or would it be more accurate to say that this information is encoded at the time of entanglement and separation itself?
First of all, I was careful when I described entanglement. I told you, while respecting locality, which means that entanglement does not allow you to transmit information. You see,
Right.
the entanglement game is of the following variety, that I am able to predict things that you will see in your lab even before you see them. But I will not be able to tell you. See, I will record in my notebook, put a timestamp for a post facto verification. I will not be able to predict or influence and tell you. So there is no communication channel that can be set up using quantum entanglement.
I did not understand that, sir. Can you clarify on it? Because
Well,
the
for
way I
that I have to get into certain technical details about entanglement and maybe give a whole talk. But if I have raised your curiosity, how we do this and still respect locality, I think purpose of the talk is solved.
could you refer any material to me or a paper to me from which I can understand this locality?
Yeah, you say no signaling. Search on Google
Huh.
quantum entanglement and no signaling. Technically, the information exchange is called signaling. So if you look at no signaling principle, that will give you material on to read on this. And you can write to me. I will send you something.
Okay, thank you, sir.
Yeah. Thank you, Prashant. The next question is from Akash Jain. Akash, are you around?
Yes, sir.
Yeah, please go ahead.
First of all, sir, good afternoon. Sir, my question is, we know that Heisenberg uncertainty principle never allow whatever science, howsoever science may be advanced, it never allow to detect the electron position and velocity at the same time. So, how is the relevance of quantum research work if the electron probability always belongs to open interval 0, 1? So always there is a question of uncertainty and unpredictability running parallelly with our research work. So,
Well, yes and no. if you read the paper by Feynman, where he constructed first time the model of a quantum computer, that's what people said, that uncertainty principle will not let you build a quantum computer. What he showed was that the way you can do this, uncertainty principle actually does not come in the way. You work with a certain basis and unitary transformations on states, and later on make measurements in the same basis. So uncertainty principle, of course, is respected all the time, but it does not lead to the kind of noise you are thinking about all the time. Because if you fix your computational basis and you do your quantum computation in such a way that answer is finally encoded in that basis, then you will be able to make measurements without any errors. So you have to cleverly manipulate things so that you read information from the basis and push your answer of the computation in that basis. Something else will become uncertain, but that you will not be interested in. At this stage, I can give you such an answer. Technicalities of, so that's why quantum algorithms are not straightforward. Quantum algorithms have to cleverly circumvent the aspects of measurement based collapse and also aspects of quantum uncertainties which are generated in such process.
Okay. Thank you, Akash. The next question is from the YouTube. It is from Shraddha, who is doing her BSc B.Ed in Khalsa College. She says, scientists claim for existence of 36 extraterrestrial alien civilization. What about whole different technology, one based on entanglement?
Well, see, there is science and there is science fiction and there is speculative science. So, of course, there's a very serious efforts are going on to find out Earth-like planets and extraterrestrials and life outside in the rest of the universe, and it's an exciting area. Now, I don't work in that area directly, though I'm aware of this area. But in principle, quantum entanglement can exist over very long time length scales, and quantum entanglement can exist across parts of the universe. However, as I mentioned, it cannot be used as a communication channel. So even if I make any predictions using quantum entanglement about part of the universe which is very far away, how am I ever going to know that these predictions are correct? For that, I have to connect with that part of the universe. And in the process of connecting with that part of the universe, I'll have to use light or other means, which of course, if the other that part is a million light years away, will take a million years to do. So verifiable predictions of entanglement will not be possible. But in principle, yes, entanglement could exist in different parts of the universe.
Next question is from Shreyas, who is a second year BSc student at Ferguson College, Pune. His question is, does locality principle disturb the quantum entanglement on large distance?
No. No. What disturbs quantum entanglement is the process of decoherence. What happens is that if two systems are entangled, say I have a quantum system which I have kept very nicely with me, and you have a quantum system which you have kept very nicely with me, and they're entangled. What happens is over time this entanglement degrades, because what happens is my system locally interacts with the things, my laboratory, photons, stray light, so on, and those processes disturb my system. And when my system is disturbed, its entanglement with your system is also disturbed. So that's how entanglement degrades over time. But it doesn't degrade because of the locality principle. So just distance doesn't make it degrade anyway. That is the great thing about quantum entanglement. You know, so it is the time and the random processes which my system undergoes over time which leads to degradation, not the distance between two locations.
Next question is from Yash Rana, former student of IISER Mohali. He says, can you tell me more about how quantum mechanics would influence biological systems?
Well, I will give you a short answer. You search, I gave a webinar on this organized by outreach talk organized by another organization. It's called Quantum Biology. They have put it on YouTube. So you can have a look at that, where I've talked about exactly this subject, how quantum mechanics is influencing biology. To give you a short answer, yes. What we think is that a lot more places within biological systems we are going to see quantum motifs playing role than what we thought earlier. Earlier, we were thinking like Landauer, if temperature is room temperature, if length is certain microns, quantum mechanics is not relevant. But particularly in the photosynthesis process of bacteria which live in low light, and also the avian compasses of certain birds in Europe. Which one is? I'm forgetting the name of the bird, which navigate in a way very different from just aligning with the magnetic field. And the whole olfaction, the sense of smell. There are three very important things which have happened in the past years where quantum ideas have been used to explain these things. So sense of smell now has a quantum explanation. The earlier vibrational theories are not able to explain it. So short answer is yes. And you can listen to my webinar.
Next question is from Maria, who is an MSc student from Department of Theoretical Physics at University of Madras. The question is, if it is not light that passes information in an entangled system, can you explain then what physical phenomena makes us to get the information about two qubits at the same time?
Well, first of all, it is not a communication channel, which I have already been saying. So entanglement is again, like for example, very difficult to imagine that a single electron is in the entire p orbital. The word is maybe more complex and more bizarre than we think, because as Delbruck had put that what we call intuition is basically evolutionary experience, come out of evolutionary experience over long periods of time living in a world of certain dimensions. So we feel this is natural, this is how things are. But already we know that things can be very different. So there is no physical, when I make a measurement on my qubit, nothing physically is traveling from there to the other qubit. But so in some sense, the information is encoded in a way which is non-intuitive. There is a certain correlation which I cannot explain using regular intuitive ideas about correlation. Let me put it that way. Quantum correlations can have a very different nature compared to the way we think about correlations. But one thing is very clear, that entanglement cannot be used as a communication channel.
Next question is from Sadat Salman. He says, why did physicists prefer Copenhagen interpretation over Bohmian mechanics, which is a deterministic theory, resolves the measurement problem, and where probability is not fundamental?
Yeah, you see, that's a very interesting question. So the problem with, well, I'm not that much against Bohmian theory. I am not a fan of Copenhagen either. However, to avoid probability, the Bohmian interpretation brings in non-locality, which means in the Bohmian world, things can influence each other at faraway distances simultaneously. That is an even more bizarre thing to accept. You see, I mean, I'm doing an experiment here, and you sitting at home are spoiling it. That's like saying that, you do some tantar mantar and I lose my life. So that is the kind of non-locality you have to bring into Bohmian description. So yeah, it is a deterministic description, but deterministic non-local description. So the real thing comes from Bell. Bell in 1964 proved a theorem called Bell's theorem, which said no description of the world which is based on local hidden variable, local deterministic theory can be compatible with quantum prediction. So you have to give up one. Either you give up non-locality, then you have to bring in probabilities in a fundamental way, or you give up probability and you want to remain deterministic, but then your deterministic phenomena will be non-locally connected with things happening elsewhere. So you have to become very non-intuitive one way or the other. The choice is yours. So many people who are realists, they say, oh, we want deterministic world, however bizarre it might be. But then there are the people who think that, what is so great about determinism, right? Determinism, in some sense, also originates from idealistic philosophy that, somebody is put the rules, somebody is dictating everything and so on. But a large number of people don't think about that somebody. So therefore, probability could be as nice a thing to embrace. I would prefer to embrace probability and write down equations for probability so that I know the uncertainties involved instead of thinking that, my outcome is influenced by your tantar mantar far away in the world.
Next question. The name is not very clear, but the question is, why 0-point energy cannot be harnessed?
Well, by the very fact that it is 0-point energy, you can't, to harness this, you'll have to lower it. And that the whole idea is that you can't lower energy beyond that. Right? If I take away energy, I'll have to reduce energy, but that is already the minimum. So how can you take from if the minimum bank balance is, bank says 1,000 rupees, you can't go and withdraw that money, right? That is the minimum the bank keeps. Similarly, the 0-point energy is the minimum allowed energy in the system quantum mechanically. So you can't just harness it.
Okay. Maybe we'll take 2 more questions or 3 more questions and then stop.
That is up to the host. Yeah.
Next question is Aditi Joshi. Can you please talk on what kind of decoherence comes in macroscopic bodies?
Yeah, see, decoherence is a very, very important and detailed topic. See, what happens is, in a very simple way, more ways decoherence, where does it come from? It comes from random interactions. Random interactions depend on 3 things. One, it depends on your environment. What are the things in the environment in which you can interact? Second is, how many ways can you interact? Because there may be things in the environment, but like a photon passes through glass, doesn't interact with any of the atoms in the glass, just goes to the other side. There's no decoherence of photon passing through glass. So ways, so certain interactions possible. And the third one is, how many of you are there? More are you, one or the other will interact. So your question is in the third domain. Larger object has many more atoms, so any one of them can go and do a mischief and interact with someone. You see my point. A larger object has more degrees of freedom. Each degree of freedom has a possibility of interacting with the environment, and that leads to more possibilities for decoherence.
Okay, so the last question from Aghav Shah. For Grover's algorithm, we need data to be stored in a database. How do we create a quantum type data and store it in a database? How will the database not stay unaffected?
Well, so quantum memories, we have to build quantum memories, which means that I take a qubit and I put it in a certain state and it remains in that state. So people are working very hard to build quantum memories and how long they will last and so on. Yes, I agree. So we have to store information quantum mechanically before we can process it quantum mechanically. So yes, building quantum registers is part of building a quantum computer. And they can get affected, decoherence, various other processes can come in. So a lot of work is going on how to build stable quantum memories.
So I'm sure there are many other questions, but because of lack of time, we will close here. But you can ask your questions through email. I have shared the email of the Dean Outreach in the Zoom account. You can write to deanoutreach@iisermohali.ac.in if you have any questions. We will pass it on to Professor Arvind, and he will get back to you with his answers. The second thing I wanted to request is that this is the second talk in our series. I'm sure that you people would like to hear many different topics. So if you have suggestions about the topics that you would like to listen to, please write into us. We will try and get people to talk about those topics. Finally, I would like to thank the team behind this who are refusing to come on screen. There is Dr.
Maybe
Amit.
They should come for a minute at least.
Well, I have requested and they have said they would like to stay.
Amit is here. Great.
There is Dr. Amit, Dr. Mahua. No? You want to stay behind? Okay, Dr. Amit and Dr. Mahua. This is the team that has actually been doing all the work. So a big thanks to both of them. Thank you, Arvind. This was a very nice talk and very nice interaction. And we hope to have the third in the series very soon. Thank you all. Thank you so much.
I thank you all for organizing it.